Good evening, students. Welcome back to my channel, which is Pandu. Today's lesson is a continuation of work power energy. Today we will learn about the work energy theorem. First, we discuss about the work energy theorem. What is work energy theorem? If we apply a force on a body, it will move. That we've done some work, and that work done is change in its kinetic energy. That is the work energy theorem. Now let's write that work energy theorem. Work energy theorem. Now to prove it, work energy theorem. Now to prove the work energy theorem. Now to prove the work energy theorem, we know that for the constant force, F is equals to m into A. We know that. Now here m, we can write the A in the form of dV by dt. That is dV by dt. Now let's change it. M dV by ds into ds by dt. What is ds by dt? ds by dt is the velocity. So we can write m dV by ds into v. F is equals to. That's the format. Now let's move to the work done. dW, for the small quantity of the work done, dW is equals to m dV by ds into v, that is the force, and here into ds. Now we will certainly get m into dV into v, dV into v. Now the work done, to have the work done, integrating both sides, that is integration of dW is integration of the initial velocity to the final velocity, m into v into dV. Okay. Now the work done, W is equals to m into u to v dV. Now erase it. Now here that is equals to the integration of v square by 2. So u to v, that is equals to m into v square by 2 minus u square by 2. So here we will certainly reach the result. W is equals to half m v square minus half m u square. That is the change in the kinetic energy, which is equals to the work done. So work done is equals to change in the kinetic energy. Now we can write it in the form of W work done is equals to Kf. What is Kf? The final kinetic energy minus of Ki, that is the initial kinetic energy. Okay. Now we'll do the same proof for the variable force. For the variable force, here we consider the work done along the x-axis. Here we consider the work done along the x-axis. So here W is equals to integration force along the x-axis Fx, here dx. Okay. Now what is Fx? That is equals to integration m ax dx that is equals to integration m. Ax means dvx by dt into dx. Okay, now that is equals to integration m dvx into dx by dt. So here dx by dt is the vx, that is the velocity of the particle along the x-axis. So here that is equals to integration m dvx into vx. Now here we consider the limit ux to vx, and certainly integration after it we get half m vx square minus half m ux square. That is the work done is equals to change the kinetic energy. What it is the work energy theorem. Now let's start to discuss about the potential energy. Potential energy. Now what for the potential energy comes for? Due to configuration and due to the position, we get the potential energy from the foot. And also if we consider an elastic and stretched it will preserve the elastic potential energy. Now what is gravitational potential energy? It is a duster that's position is on my hand and lift it to a height h, then the gravitational energy, then the energy, that is the potential energy stored in that duster is the gravitational potential energy. What is the expression of the gravitational potential energy? The expression is mg into h. mg into h. Now, to find the relation between the conservative force and the potential energy, relation between conservative force and potential energy PE, and the potential energy PE. Now here we should consider that the delta W is the work done. Delta W is the work done. That is equals to A into dx, and delta U is the potential energy, that is equals to minus delta W. Now putting delta W here, we get F into delta x, F into delta x. Now here F x we should consider along the x-axis, Fx is equals to minus delta U by delta x. Now taking the limit, Fx is equals to minus limit of delta x tends to 0, that is delta U by delta x is equals to del U by del x, del U by del x. Now similarly we will get Fx is equals to minus del U by del x, Fy is equals to minus del U by del y, and Fz is equals to minus del U by del z. So here we can write F vector is equals to Fx I hat plus Fy j hat plus Fz k hat. So putting that minus del U by del x I hat minus del U by del y j hat minus del U by del z k hat. So here that is equals to minus I hat del x plus j hat del y plus k hat del z into u, and that is the gradients, that is equals to minus gradients of u. F is equals to minus gradient. Okay students, now to discuss the potential energy stored in a spring. Now let us consider a valve, that is the valve. A spring is attached to a block and the valve. If we apply the force, that is F, it will extend to X. So here F is equals to K into X. What is K? K is the stiffness constant. Now to find the work done, dW for the small amount of displacement, A into dx. Now putting F equals to kx dx dw is equals to, so integrating both sides, integration 0 to x kx dx, that is equals to k into x square by 2, that is equals to half k x square. What is that is the elastic potential energy, that is the elastic potential energy stored in the spring. Okay, that is all for the day. Please read it, and any kind of question, please inbox in my comment box. And goodbye for the day. Stay tuned. Please share, subscribe and comment, and ultimately like my videos.